In this video, we're going to talk about the multi-stage transistor audio amplifier circuit. Now, this circuit requires two transistors. You could use more than two, but two will be enough for our purposes. We'll call it Q1 and Q2. These are NPN transistors. This is the base, the collector, and this is the emitter pin of the transistor. Now, in this video, we're not going to focus too much on the math, but more on the concepts behind this particular circuit. Now, the first three capacitors that you want to be familiar with are these three capacitors, C1, C2, and C3. These are coupling capacitors. They're designed to block DC, but to allow the passage of an AC signal or a voltage variant signal. Now, the values of C1, C2, and C3, ideally speaking, you want them to be greater than 1,000 microfarads if you're using this circuit to amplify an audio signal. If you're using it to amplify a high frequency signal, then you could use a much lower capacitance. The formula for the capacitive reactance is 1 over 2 pi Fc. So as the frequency increases, the capacitive reactance decreases. So if you want to amplify a low frequency signal, such as a sound wave that has a lot of bass, then you want to use large values for C1, C2, and C3. Just to give you some numbers, let's say that the frequency is 100 Hertz. If you were to use a capacitor that's 100 microfarads, the impedance will be 15.9 ohms towards that 100 Hertz signal. But if you were to use, let's say, a 1000 microfarad capacitor, the impedance will be 1.59 ohms. And so by increasing the capacitance of the coupling capacitor, you can decrease the impedance of low frequency signals. Because when dealing with an audio amplifier, the frequency can vary from 20 Hertz to 20 kilohertz. So large capacitors will allow the low frequency signals to pass through. Now the next resistors that we're going to talk about, actually, I need to add some other resistors here. These resistors are not required, but you could use it to limit the input voltage that's applied to each stage. Let's call this R1 and R2. We're going to call this R3, R4, R5, and R6. Now, R1 and R2 are potential meters. Notice that R1 and R4, they form a voltage divider network for the first stage of the amplifier. Now, the purpose for this is to reduce the input voltage, because if the input voltage is too high, it could drive Q1 either into cutoff or into the saturation region, which will create distortion of the signal. So R1 is used to decrease the input voltage if needed. If the input voltage is too low, you don't have to worry about adjusting R1. You can keep it at its maximum value. But if the input voltage is too high, you want to decrease the resistance of R1. And the same is true for R2 as well, because the voltage generated by Q1 may be too high, and so R2 can reduce the voltage generated by Q1 so that it doesn't create distortion in Q2. It doesn't drive the second transistor into the cutoff or saturation region. And so by having these two potential meters, you don't have to worry about the exact values of R3, R4, R5, or R6, because you can adjust R1, R2 to make sure that the input voltages that is applied to the base of Q1 and Q2 is not too high, so that you could reduce distortion. Thus, R1 and R2 can be used to control the volume of the audio amplifier. Now, R3, we're going to give it a value of 500 kiloohms. And R4, I'm going to give it a value of 100 kiloohms. If two transistors are needed to amplify a signal, chances are the signal at the input is very, very weak. So the base current for Q1 doesn't have to be that high. That's why I can choose a large value for R3. Now I want R1 to be 10 times the value of R4 so that R1 can reduce the input voltage by a factor of 10 if needed. So if the input voltage is too high, I can greatly reduce it to minimize distortion. Now let's call this RC, the collector resistance, and RE, the emitter resistance. Another thing that you need to keep in mind when designing an amplified circuit is the HFE, or the beta value of the circuit. Beta is the ratio of the collector current to the base current. And for a typical NPN transistor, this could vary between 100 and 300. So that tells you the current gain of the transistor. So what I'd like to do is make sure that the base resistance, which in this case R3, the ratio of the base resistance to the sum of RC and RE is equal to or greater than beta, so that the current gain is not limited by those resistors. So let's say, for instance, if RC was 50K and R3 is 500K, and let's say RE is relatively small compared to RC, then beta will be limited by these two resistors. So based on that example, the beta for that circuit with those values of R3 and RC should be around 10 if you don't take into account the other resistors, or assuming that they're negligible. And that will greatly limit the current gain, where the beta could be as high as 300. So if you want to get the maximum current gain for these transistors, you want to make sure that the ratio of the base resistance, R3, relative to the collector and emitter resistance is greater than or equal to the beta of the transistor, if you want to maximize the current gain of the circuit. Sometimes the current gain is not that important, but if it is, then that's one thing you want to take into account. Now, the other two capacitors, C4 and C5, they are bypass capacitors. What they do is they bypass the emitter resistance. And this has the effect of increasing the voltage gain of the circuit, but it can also potentially increase distortion, because if the voltage gain is too high and you apply a high input voltage to the base of this transistor, it can lead it into cutoff or saturation, thus creating distortion. So it's important to understand that adding C4 and C5, there's a trade-off. You'll increase the voltage gain, but you could potentially introduce distortion. But if you do introduce distortion, you could reduce the voltage by using the potentiometers R1 and R2. So that's the purpose of C4 and C5. The voltage gain of a transistor amplifier is the ratio of the collector resistance to the AC emitter resistance. Now, by introducing C4, you bypass RE. Without C4, the voltage gain would be the AC emitter resistance plus capital RE, the emitter resistance. But by introducing C4 and C5, this is eliminated, thus increasing the voltage gain of the circuit. Now let's adjust our RC and RE values. So since R3 is set to 500 kiloohms, I want RC and RE to be less than 100 times this value. So if you divide that by 100, you get 5 kiloohms. So if I were to use a value of 1K for RC and 1K for RE, then beta could be at most 250. If you divide 500K by 1K plus 1K, or 2K, that gives you 250, which is a decent current gain for the first stage of the amplifier. Now, beta won't be exactly 250, but at least it gives me a ballpark figure of what it could be. Now let's talk about R5 and R6. Let's say that the input voltage is 1 millivolt. And let's say at the output, the voltage is increased to 100 millivolts. It may not be those exact numbers, but for the sake of illustration, let's say that's what it is. So now that we have a higher voltage, that will induce greater currents flowing in this region of the circuit. So therefore, we want a larger base current to be applied to Q2, which means you want R5 to be lower than R3. So because we're dealing with higher voltages in the second stage of this circuit, we're going to make R5 lower. I'm going to make it 47K. You could make it 50K if you want to, but you usually don't find a 50 kilo ohm resistor. Chances are you'll find a 51 kilo ohm resistor. And for this, chances are this will be a 510 kilo ohm resistor. Now I'm going to make R5 equal to R6. Here I didn't do that because it really wasn't necessary, because the input voltage here will be very, very low. But now the voltage at the second stage will be higher. So I want VB to be higher. That is the potential at the base. Because if VB is too low, then a high input voltage could drive it to cutoff or saturation. Now let's say that our collector supply voltage is 12 volts. R5 and R6, they form a voltage divider network. If the transistor wasn't there, and if R2 wasn't there, then the potential at point B would be half of 12 volts, since these are equal. So ideally that would be 6 volts. However, because of Q2, it's going to draw away current from the voltage divider network. So the actual voltage will be less than 6 volts. It could be 5, it could be 4 volts, but let's say it's 4 volts. If VB is at 4 volts, then the input AC signal at this point shouldn't be more than 4 volts. So you don't want the AC signal to be more than 4 volts at point B, because the negative half cycle could turn off Q2, which will lead to distortion. And so that's why R2 is so helpful. It can reduce the input voltage that's applied to Q2. Now, the next thing you want to take into account is the maximum VBE voltage that should be applied to the transistor. For the 2N2222A transistor, if you look up the datasheet, the maximum VBE voltage is 6 volts. Now, since this is 4, this is going to be 3.3, because typically the voltage drop is usually around 0.6, 0.7. So you don't have to worry about that in this case. But you don't want VB to be too high, which could create its own problems, so just keep that in mind. But typically VBE will have a voltage drop of 0.6 to 0.7 volts. Now the next thing we need to talk about is the value of R2. Notice that R1 is 10 times the value of R4, so that we can be able to reduce the input voltage by a factor of 10. You could do the same thing here. So in this case, I would use a potentiometer of 510 kilo ohms. Now, if you use the same potentiometer of 1 mega ohm, it won't be that bad. You'll just have the ability to reduce the input voltage that's applied to Q2 by a factor of 20 instead of a factor of 10. So that's not really a big problem. In fact, that's not a problem at all. Now let's call this RC2 and RC1. During the second stage of the transistor, you want to make sure that the current gain is relatively high. The first stage is useful for increasing the voltage gain, but the second stage, you want it to increase the voltage gain if needed, but also the current as well. And so to increase the current gain, you want to decrease the value of RC2. So instead of using 1 kilo ohm, perhaps we want to use something like maybe 100 or 200 ohms. Let's use 220 because that's a common resistor. And for RE2, you could use the same value, or you could use something less, maybe like 33. So If we were to increase the value of RC, it could be any one of these two. If you increase it, the current gain of the amplifier decreases. Increasing the collector resistance will mean that there's less collector current flowing through the collector and the emitter of the transistor. And so ultimately that will reduce the current gain. So that's why I don't want this value to be too high, because I want to have a high current gain in the second stage of the amplifier. But there's a trade-off too. As we said before, the voltage gain is equal to the AC collector resistance divided by the AC emitter resistance plus RE. Now granted, we've bypassed RE, so we don't need to worry about that. Now, RC is basically the collector resistance in parallel with the load resistance. The load resistance is going to be the resistance of the output circuit. So hopefully that's very high. But nevertheless though, RC is directly related to AV. So if you increase RC, you can increase the voltage gain of the circuit. So a high RC value leads to a high voltage gain but a low current gain. And so there's a trade-off here. So what do you do in that situation to increase the power gain of the circuit? Well, you could change the type of amplifier that you're dealing with. What we have here, particularly in the first and the second stage, is known as a Class A amplifier. A Class A amplifier has a maximum efficiency of 25%. Typically, it's going to be lower than 25%, but that's the maximum theoretical efficiency. Now, for the first stage, we don't really have to worry about efficiency because the input signal is very weak, and so the energy that's used by the power supply for the first stage of the amplifier will be relatively low. So efficiency is not very important for small signal analysis. If you're trying to amplify a signal that's very, very weak, you really don't need an efficient amplifier. But now, when you want to increase the power of a signal, efficiency becomes more important. And so to improve the efficiency of the second stage, instead of using a Class A amplifier, we could use a Class A transformer coupled amplifier. So what I'm going to do is I'm going to replace RC2 with a transformer. So C3 won't be needed in this case because the output will now be taken from the secondary side of the transformer. And this is going to be the load resistor, which we'll call RL. Now let's talk about using an inductor here, because both an inductor and a transformer, they're made up of coils of wire. So this section acts as an inductor. Now an inductor has a low DC resistance, but it can have a high impedance towards AC signals with high frequencies. The impedance of an inductor is 2 pi FL. So as the frequency goes up, the inductive reactance goes up. So there's more impedance towards high frequency AC signals. Now, because the DC resistance of inductors tend to be low, RC, in this case RC2, which you could think of as the DC resistance of that inductor, because it's low, that's going to increase the current gain of the circuit. So that means we can get a larger collector current flowing through Q2. Now, the second thing is impedance. For AC signals, the impedance is high. So increase in XL has the effect of increasing the voltage gain of the circuit, particularly for signals that have high frequencies. Low frequency signals, the ones that have a high base, they're going to have a lower voltage gain because XL is lower for those signals. But for the high pitched sounds with higher frequencies, those signals will have a higher voltage gain because the impedance is higher. And so the effective RC value will be higher for those frequencies. So that's the one downside of using this transformer, is that it'll favor high frequency signals, but it will reduce the amplitude of low frequency signals. So you may get a more high pitched sound. But one advantage of using a transformer is the efficiency. The theoretical efficiency of a transformer coupled Class A amplifier is 50%. Now, in practice, you may get an efficiency of less than 40%, but nevertheless is better than a regular Class A amplifier. And so you can get more power at the output. And also, if you use a step-up transformer, let's say if the ratio is 1 to 10, you can increase the output voltage big time. With a ratio of 1 to 10 in terms of the number of turns in the coils of the primary and the secondary part of the transformer, the voltage will increase by a factor of 10, but the current will be reduced by a factor of 10. So that's one of the advantages of adding a transformer to the collector of Q2. You could generate very high voltages at the output of that transformer. And also, the amplifier is more efficient. Now, even though the use of the transformer will favor high frequency signals over low frequency signals, there's things you can do to compensate for that. Now, one way in which you can increase the base of the signal at the output is by adding a capacitor between between ground and the collector of the transistor. So if I put a capacitor here, what's going to happen is it will filter out high frequency signals, but it will allow low frequency signals to pass through. So just to be clear, adding C6 will reduce the voltage gain of both low frequency and high frequency signals, but it will have a greater impact on high frequency signals. So as was mentioned before, the transformer favors high frequency signals. The capacitor favors low frequency signals, so you have a balance. So if you increase C6, then what's going to happen is the output will allow low frequency signals to pass through. It will sound as if it has more bass. If you decrease C6, you will get a more high-pitched sound. So by adjusting C6, you can adjust the bass of the sound that you hear at the output. So you don't want C6 to be too high. Maybe like 1 microfarad or 0.1 microfarad should suffice. You can test out different values, but if it's too high, it will greatly reduce the voltage gain. So the voltage gain of the entire circuit will depend on the value of C6. So that's basically it for this particular circuit. So now you know how to design a multi-stage transistor audio amplifier circuit. Now there's one more thing I do want to mention. The overall voltage gain is the ratio between the output voltage and the input voltage. And it's also the product of the voltage gain of the first stage times the voltage gain of the second stage. So that's the overall voltage gain. So let's say if the voltage gain at the first stage is 100, and let's say the voltage gain at the second stage is 50, then the overall voltage gain up to this point will be 100 times 50, or 5,000. This is not including the transformer, because the transformer can also increase the voltage by a factor of 10, but decrease the current by a factor of 10. So if it increased the voltage by a factor of 10, you're looking at a voltage gain of 50,000 overall. Now chances are it's going to be less than that, but that's how you would calculate the voltage gain of a multi-stage amplifier. It's the voltage gain of the first stage times the voltage gain of the second stage.